Okay, good afternoon, everyone. Shall we start? Okay, very first thing is about a presentation schedule. I changed it a little bit, okay? This is because I checked the how many lectures we can have and how many tutorial time we can have over there. And I find we'll start talking about a polymer this afternoon, and then on the Thursday we'll have a test on the steel. The next week I'll be away, and then on the 28th, the morning and afternoon sessions, I will try to finish the polymer. Then we're going to have a test on polymer on 30th, which is Thursday again. And then we have one more day left for this semester, which is the Tuesday on the 4th. So on the Tuesday and the 4th, I planned to have in the morning, we're going to have presentation for the two groups, group 1 and group 2. And then in the afternoon, we're going to have groups 3 and 4 to do the presentations. So the original plan was the group 1 and group 2 will do the presentation on the 30th. So I just pushed to the 4th of April. Okay. This schedule is posted on the website, posted on the Teams already. Okay. And I didn't. I don't think I deleted the older one. So now I'm gonna delete the older one. And the older one was on the. This one was on the 30th, so I'm gonna delete that older one. Okay. So in case you forget, you just go to the Teams, and then you can dig out of the presentation date, that PDF file. Delete. Okay, so any questions about the plan for the next 2.5 weeks? And I will send out the announcement about the test on Thursday, March 30th, and for the polymer module. Okay. Any questions over there? If not, we're gonna start to talk about the last module, okay, which will cover the polymer there, okay. I just signed 1 or 2 to goodness. I think I signed it to Daniel, Mike. Are you there? No. Just see if you was about this. Basically nothing. Okay. Thank you. I don't have to repeat those. Go ahead. Oh, come. I think I did it. I did it. Hold on. Let me just try one more time. And share the screen. I don't know.
Can I show you? I think it's an issue with the computer.
Yeah,
Is this your normal desktop?
So what is it?
Leave for a second.
Should I stop the sharing?
Yeah, and then if you go to settings,
But, what is that?
yeah, the gear and display.
So I should choose it too. Is that?
No. May I? May I search something for a second?
Okay.
Oh, no, sorry, that's the wrong one.
I thought it was
That's,
whatever you want. Yeah, I think it's duplicate. It's
and if you, there we go. There we go.
oh, thank you. Okay. So what? Hold on, whatever. Okay, I got it. The exchanges. Yeah, that's right. Okay. I share. Did I share it already or no? Let's just do share again. Share. What's that? So I don't have to repeat the slides 1 and 2, okay? I think Daniel give you guys a good introduction, okay? So, slide number 3 and 4, I just signed to Jacob. I don't. So I signed it to Andre Stefan. Are you there?
Yep.
Yeah, I just say a few words about this one, excellent. Thank you. Appreciate it.
Yeah, so this slide is talking about the daily applications. The examples here, the PVC pipe, high density polyethylene bottles, epoxy glue, polyethylene bags, and as well as an eraser. And this slide is talking about the general properties. So for the advantages, we have advantage in weight, price, corrosion resistance, trimming, dielectricity, and elongation. And some of the disadvantages, we have stiffness, tensile strength, impact strength, maintenance, temperature, and environment.
Thank you. So, daily life, and often you can see is like the milk jar, okay, over there is one type of polymer, high density polyethylene, HDPE over there, and those plastic bag, polyethylene bag, and then glues, epoxy glue, and those PVC pipes, okay, and the erase is one type elastomer. Okay. So polymer compared with metals has some advantages and disadvantages. Very light. It's definitely a lightweight material. And price-wise, depends. Most of them are much cheaper than the metals over there. Very good corrosion resistance. You can trim them easily, and dielectricity. And some elastomers can give you a very good elongation, 300% easy, but very low stiffness in terms of modulus. And strength-wise, either tensile strength, yield strength, or impact strength are not good. And maintenance, because most of plastic age with time, and so this sometimes will won't last that long for some applications. And temperature, it cannot sustain the very high temperature. 100 degrees probably is the highest you can have over there. Environment, because the plastic hard to recycle, so it's not an environment friendly material at all. Massive Philip, there. Okay, so this table give you some detailed information about the properties in terms of density. This is basically 10 to the 3. Okay. So density wise, very light. Okay. Even for the glass reinforced epoxy, carbon fiber reinforced epoxy, the density is also very comparable to the magnesium over there. Okay. And in most of the plastics, the polymers, okay, they will have a density around 1. Okay. And the modulus wise, elastomer and the thermoplastic, these two types of, or even the thermoset, the modulus are very low, except you make some polymer-based composite. The last two, glass epoxy and carbon epoxy, those basically are the composite materials. Okay. And but if you only have the polymer itself, you have those fiber as a reinforcement in the material, and modulus is very low compared with metal. Okay. As strength wise, you compare with aluminum, steel, and cast iron, and these polymers are very low unless you have a polymer-based composite. Okay. Either use glass fibers or the carbon fibers over there as a reinforcement. And surface temperature and plastic compared with metal. Metal is normally for aluminum at least 200 degrees C, and for the steel 500 degrees C, no problem. And cast irons 300 to 400 degrees C shouldn't be a problem. But for the thermoset and the thermoplastic, they're very low. Okay, normally around 100 degrees C in that range. Okay. Elastomer, polybutene, butadiene, okay, and give you a high temperature. And composite can give you a little bit of high temperature over there in terms of service. Okay. And as I mentioned before, the weight, metal is definitely cannot compare with the polymer. Polymer is very light, and cost is low. Okay, the price is low, and stiffness is low compared with metal. So metal is good. Okay, it is strength of metal is also good. But the elongation wise, it depends what type of the polymer you have over there. For elastomer, you can have a very high elongation over there, 3 or 4 times than the original lens, which you can stretch the elastomer to. But for thermoset, thermoplastic, maybe it's not that high. And the impact strength and surface temperature definitely low on polymer. Can you see a few words about this slide? Next one. Try to use this slide to show you the polymer can use all over the place in a vehicle. Doesn't matter electrical or the gas powered vehicle over there. Okay, so exterior chassis and electrical electrons, fuel systems, hybrid electrical electrical vehicle. They also use a lot of polymers over there. Safety system, interior, and a powertrain engine for the gas powered vehicles, and the thermal management and HVAC, okay, and the transmission and drive lines over there. Okay, a lot of application. So, for example, for the exteriors, you'll be able to see the headline bezel, okay, exterior trims, okay, and the panels or whatever, okay. Bubak, are you there? Can you just see few over this one, next one? That. And so for the chassis, okay, the suspension systems, okay, they can be being applied for the tire, okay, and even some brake systems and hoses, tubing, cable, or those kind of things. Definitely, they are made by polymers. And steering systems, exhaust system over there, okay. Electrical and electrons, okay. Those components related to the lighting, okay, as a cover or the bezel or whatever over there, and they are made by polymer. And then a lot of the components related to the connector, okay, for the electrons, and those cases over there, and they made by polymer over there. And they're talking about the sensors and solenoids, okay, those stuffs. And we use a lot of polymers over there, Okay. Lance, can you just say a few words about this one, next one? Thank you.
Fuel lines and hoses and fuel system components. And the next page showing the hybrids and EVs. In the picture, it shows the battery pack structures, battery pack form, connectors, and cable jacking, electric motors, thermal management system, power control unit, and fuel seekers.
Thank you. Fuel systems, especially the fuel line. Okay. Now you're gonna say the fuel line. I sort of probably in your mind that the fuel line is made by the steel pipes or whatever over there, right? Yeah, you're true. You're right. Okay. Actually, the fuel line is quite a complicated kind of component. It looks like it's just a pipe over there, but it's not that simple. Okay. And so they use the steel sheets to load it, and they use electrical resistant welding to make the pipe, okay, and to seal it, and then they will add a coating on it, add either aluminum based or zinc based alloy to coat that steel tubing over there. Then then they will add another layer of nylon on top of either aluminum coating or the zinc coating over there. So the process itself is not as simple as you just saw it. It's a piece of the steel tubing over there. Okay. Again, this knowledge because I carried out a project for a company. They're making these kind of fuel lines over there. Okay, and because originally they use the zinc to coat it. They find that the zinc coating is not very durable, okay, and the bonding wise with the steel is not that strong, okay, so they want to change it to aluminum, okay. So I was involved over there. Then when I saw that structure over there, I did a microstructure analysis over there and realized, oh, it's not that simple as what I saw over there, okay. So the fuel line definitely has nylon coating involved over there. You have to use quite amount of nylon as a coating to protect the corrosion. I mean, and so the fuel lines, and then for the electrical vehicle, a hybrid vehicle, whatever. Okay, and you have used a lot of electrons over there, so you use a polymer as a material to do some insulation over there. Okay, and so a lot of cases over there. For the battery, okay, you can use a polymer as a case to hold those batteries over there. And also it's good to prevent any kind of fire or whatever over there, okay? And a lot of the cables over there, okay? And they are definitely coated with polymer to prevent any kind of electric shock over there, okay? And thermal management systems and definitely, okay. They use a lot of polymer over there. And I don't know electrical motors. Okay, is any polymers involved over there? I'm not so sure. Okay. Zihan, are you there? No.
Yeah, I'm here.
Oh, you're online? I can just see if
Yeah.
you was about this slide, next one. Thank you.
Okay. These are the safety system and the interior parts made by the Polymer, which include the seating system, airbag door systems, accessories, and the door systems, radar systems, safety restraint systems and the fibers for covers and the interiors. Can you go to the next slide? And also there components including the powertrain and engine systems, which includes turbocharged components, air ducts and the air induction systems, and the oil pans and the oil systems, as well as the exhaust systems and the seals and the gaskets. Also, it has the cylinder head and over sealed engine covers. Thank you.
Thank you. So the safety systems and the interior, obviously interior, I mean, the seats cover over there, we use a lot of like a fabric, fake leather or whatever, all those polymer-based material over there. And right, the carpeters in the vehicle, whatever, okay. And then the airbag door system, okay. And the steering system, even the steering wheel, okay, very often is covered by kind of rubbery kind of material, am I right? You never will touch the steel or touch the magnesium or touch the aluminum directly. It's wrapped in by a kind of rubber kind of material over there, right? So when you hold the steering wheel, you won't feel like so rigid over there, okay, right? And then powertrain, okay, air ducts, okay, and basically the duct introduce the air into the engine area, okay, and then the oil pan, okay. Now the oil pan can be made by aluminum, steel, and also polymer, okay. And then the seals basically is adhesive, is gasket, and they are made from the polymer. Okay, definitely. Mohammed, can you just say a few words about this one next one, slide 15 and 16? Okay, and so for the thermal management, HVAC, okay, and the cooling components, okay, and the system. If you dismantle the vehicle, you will be able to see this whole piece is more or less made by polymer-based material. And then the transmission drive lines, and you will be able to see the seal rings and the oil cooler hoses, okay, and those and then thrust washer, okay, and some gearbox, okay, and the cases over there are made by polymer-based material, okay. So I don't know. I think almost all of you guys took the second year material course, right? So in the second year material course, I don't know who taught you guys. Is there any like a polymer materials being covered over there? I have no idea. Okay, maybe they did, maybe they didn't. I don't know. Okay, but I did include some fundamentals information over there. Okay, maybe those information can refresh your memory or whatever over there. Okay, and so if you directly jump to the polymer, probably you will, you probably forgot what you learned in the second year, okay, already, okay? So I just grabbed a lot of slides, some of the slides to give you, maybe for those guys still remember those things being discussed in the second year related to the polymer. For you, you just think it's a recall of those knowledge. For those, for the other students, they forgot completely what is a polymer, and then these slides will reinforce your knowledge base over there. Okay, so slide 17 and 18, Sumit. Go ahead. Thank you. So what is a polymer? Okay. So polymer is coming from two words. Basically, is one is a poly, another is a mer. Okay. So poly means many. Okay, mer means repeat unit. To demonstrate what's the meaning of the polymer, I picked the three different types of the thermoplastic polymers. Okay, and given here, the first one is polyethylene. Okay, polyethylene is so if you chop off the poly, you have the ethylene over there. So what is the ethylene? Ethylene is basically consists of this 4 hydrogen atoms and plus 2 carbon atoms. Okay, as simple as that. Okay. Then somehow, so if you just have this 6 atoms over there, so the structure looks like this. You have a hydrogen. You have a hydrogen. Okay. And so this is the structure for the ethylene. Okay. Then somehow you break one of the bonds of those between the carbons over there, and then open it up, and then connect with another unit, okay, of this ethylene, okay. So you form what we call a polyethylene, okay. And then the second example is a polyvinyl chloride, okay. It's a short form is called PVC. So what happens is the ethylene unit, one of the hydrogen atoms replaced by the chlorine, okay. So generate a repeater unit is 2 carbons and 3 hydrogen, 1 chlorine, okay. And then this unit repeats and form what they call the PVC, okay, polyvinyl chloride. And then if the chlorine, this atom is replaced by another unit, okay, it's a consistence of 1 carbon and 3 hydrogen over there, okay. Then you form a unit, a kind of polymer material is called a propylene, okay, and then propylene units, you connect them all together, it's a form of polypropylene, okay. In this table, in the next few tables, I listed a whole bunch of polymer materials, okay, and then showing you the repeat unit for each different types of the polymer. For example, polyethylene, I just mentioned, this is the repeater unit, and then for the polyvinyl chloride, and this is the repeating unit. And then if the hydrogen is all replaced by fluorine, okay, then you form the polytetrafluoroethylene, okay, in the short form PTFE, okay. And then the one of the hydrogen, okay, in the ethylene is replaced by the unit, sort of a group of the 1 carbon and 3 hydrogen over there. Then you form another type of the polymer. It's called a polypropylene. Okay. Then one of the hydrogen, if it repeats by the ring unit, I'll show you the ring unit in the next slides, next maybe 2 slides, and form another group of the polymer polystyrene. Okay, short form is called PSO. Okay? And 19. Owen Mark, are you there? And can you just see a few words about this slide, next slide? Thank you. So for the polymer with kind of complicated repeater unit, and so one of them is called polymethyl methyl acrylate, okay, in short form of PMMA, okay. And then the repeater unit consists one of the hydrogen is replaced by the 1 carbon and the 3 hydrogen, and another hydrogen atom over there was replaced by the carbon and oxygen, and also carbon with 3 hydrogens. It's a very complicated kind of repeater unit. And then the funnel formaldehyde, okay, in the short form of bakelite, okay. And the bakelite, the repeater unit is with a ring structure over there and connected to a whole bunch of other like a subgroup system over there, and with 1 carbon and 2 hydrogen, and with oxygen and hydrogen. And so the bakelite is quite a complicated polymer with the repeater unit is quite a complex kind of structure over there. Then the polyhexamethylene and adipamide, okay, the nylon 66, okay, and the structure is quite. Even the repeater unit itself is quite a long structure over there, okay. There's a nitrogen involved over there and carbon over there as a main chain structure over there, and then connected to not only the hydrogen, but also the oxygen over there. Okay. Then polyhexamethylene adipride or nylon I just mentioned on the previous slide, this been repeated. And then the polyethylene terrazole late, okay, it's called in the commercial name very often, which is called polyester, okay. In the short form, it's called PET over there. And the structure, the repeat unit, okay, with a very complicated kind of structure with a ring structure over there, and then a carbon and oxygen, and then you will have not only the hydrogen connected to the carbon in the key um, um, key line structure over there, and I also have a hydrogen oxygen involved over there. And polycarbonate, in short form, they call it PC. You have like a 2 rings involved in your repeater unit. It's quite a just too messy over there, I would say. And then for the ring structure, they call the aromatic ring over there. Is basically you have like 6 carbons over there to form a ring over there, and then 3 carbons in this ring is connected to the other carbon with a double bond over there, and the other 3 carbons with a single bond connected to the other carbon over there, and then the carbon will also connect to the 4 hydrogen atoms in this ring structure over there. Okay. Size 21, 22. Hey there, are you there? And just say a few words about this size, the next one. Thank you. Thank you. So 3 bullet points put it here and give you some general information about polymer. So the polymer you can have is basically sometimes they use a different name over there. They call it plastic, they call it rubber, they call it adhesive or whatever. Okay, and all these whatever the name you heard over there, we can classify them as a polymer over there. We can have over 15,000 different types of polymer, so it's very difficult for you to remember all the names of all those polymers. Okay, and can be classified into 20 different family. It depends how you classify them. Okay, and they are light, general, and a corrosion resistant material with a low strength and a toughness. Not suitable for a high temperature application. Okay, cheap, inexpensive, and can be easily formed in the variety of the shape and the designs. Okay. So the basic structure of the polymer. So as I just mentioned, you basically try to break up what they call a monomer. Okay, and right, remember the ethylene, and you break the double bond, one of the double bonds of the carbon, and then you connect those repeating units together and form a polymer over there. This I mentioned already. Okay, you connected them together and then form a chain kind of structure over there, and then you will get the polymer over there. So basically, you need a carbon involved over there, okay, in the polymer material, okay. And from the valence series, because carbon has 4 electrons in its outer shell, okay, and so a carbon can share those 4 electrons with other atoms over there, either hydrogen, carbon, nitrogen, oxygen, or whatever over there, okay? And to through the either covalent bonds and other type of secondary bonds or whatever. We're going to talk more about the bonding structure later on, okay? And then form a structure, okay? And which is needed for to establish polymer material over there. So you have carbon over there. If the carbon is 4 electrons in its outer shell, okay, the carbon can connect to 4 hydrogen atoms over there, and to establish a stable kind of bonding structure over there. Sam, are you there? I can just see if it was about this side. Next one. Okay. Thank you. So because the hydrogen only has 1 electron in its outer shell, okay, and then this 1 electron, if it shares with the carbon over there, so you basically need 4 hydrogen to connect it to a carbon in order to establish the stable bonds over there, okay. So if you have a structure looks like this one, 1 carbon connected with the 4 hydrogen atoms over there, and the kind of material you can have is basically the natural gas. It's called a methane, okay. And so this kind of structure over there is very light, okay, because the carbon, what is the atomic weight of the carbon? 12. Hydrogen is 1. Oh, hydrogen 2, I was saying. And then it's very light, okay. So that's why it's only can give you a form of this kind of material is a gas over there, okay. And then if somehow you use this structure and to connect them together, okay, get rid of those 2 carbons over there, connected with, get rid of these 2 hydrogens over there, and connect with the carbon over there, then the story probably will be changed over there, okay. And for example, if you have a structure which has 2 carbons, 4 hydrogens over there, I just mentioned before, it's called ethylene, okay, ethane, okay. And again, with the 2 carbons, 4 hydrogens over there, the overall atomic weight of this unit is very light. So basically, the ethylene is a kind of the gas, okay. It's a colorless flammable gas, okay. Then so this give you a structure, what we call is a mono, okay. This is not a mer, okay. We call this is a mono, okay. So somehow you break one of those double bonds connecting these 2 carbon atoms. So now you have a structure looks like this, okay. This is what we call the mer, okay. So don't be confused by these 2 different concepts. What's called a monomer, what's called a mer over there, okay. So then you connect all those mers together, okay, link the carbon to the carbon, and then you will form polyethylene. Okay, then polyethylene will become a solid kind of material over there. It's not gas anymore. Okay, because the atomic weight of the polyethylene will be much heavier than the ethylene itself over there. Okay. And so that's what I said. If two hydrogen atoms are removed and the carbon decided to bond with two other carbon atoms, then it can be seen a very long kind of chain structure can be formed over there. And the carbon atom bonded with the two hydrogen atom can be considered as a building block, the repeating unit or whatever you call it, which is a mer over there. Okay, these units made up monomer, which are the repeating units. In the molecular chain structure, a series of the monomer basically should be a series of mers being connected to each other and form a molecular chain over there. This basically, you have thousands of molecular chains put together, and then you form a piece of the polymer. In this case, we call it polyethylene. Abdullah, are you there? Can you just see if you would over this one, next one? So functional group, okay. So basically, is you try to use other type of the atoms or other type of the molecular structure to replace one of those hydrogen involved in chain structure of the polymer. Okay, so the reason why they want to use other type of the atom or other type of the molecular structure to replace those hydrogen in the chain structure is because they want to change the property. They want to manipulate the property of that piece of the polymer. Okay, as simple as that. So here the example is with the chlorine to replace the hydrogen over there. And so form the monomer is what we call the vinyl chloride. Okay. And they call the vinyl chloride the monomer. It's VCM. Okay. Or sometimes they call the chloroethylene. Okay. And then with this monomer, if you break one of those double bond, okay, which connecting to carbon atoms over there, okay, and then you will generate a mer. And you connect all these mers together, and you form a polymer material. It's called polyvinyl chloride, which is a PVC over there, okay. And obviously the PVC compares the polyethylene is much strong, okay. And then you can use the polyethylene and polyvinyl chloride to make the pipes because they're very rich, and then you may say, okay, why all of a sudden it's become so rich? Okay, compare the polyethylene. Okay, yeah, because I believe the chlorine atom compared with hydrogen is much heavier. Okay, So basically add a lot of heavy atoms over there to replace those light atoms over there in the chain structures. And then you add thousands of those chains together, not thousands, millions of those chains together, form a piece of the material. You probably can imagine, okay, those, and then basically you introduce millions of those heavy elements. I'm not trying to compare with the metals, okay? I just want to compare with the hydrogen. Chlorine is a heavy element over there, okay? And then obviously will increase the strength of the chain structure over there, okay? That's what I mentioned under this first bullet point. And then you want to further change it, okay? The chlorine you want to replace by another structure over there, which consists in 1 carbon and 3 hydrogen over there, okay? And you get rid of the chlorine over there, and then you form another type of the polymer material. It's called a polypropylene, okay? The PP over there, okay? So basically you use 1 carbon and 3 hydrogen molecule, okay, to replace that chlorine in this merge structure over there, okay? And again, the material will change its properties significantly. Through.
Yes, Professor.
Okay, just see if it was over 27 and 28.
Okay. Selective combination of monomers. A polymer can be composed of a combination of different monomers. A polymer composed of a single type of monomer is known as homopolymer. A polymer composed of 2 or more different types of monomer known as copolymer. A copolymer is analogous to metal alloy. Arrangement of polymer chains. A polymer is a series of long chain molecules composed into a complex arrangement to make a solid. There are 2 possible arrangements of the molecular chains. One is crystalline and another is amorphous. For the crystalline, molecules arrange themselves neatly to have long range orders, and for amorphous, molecules are randomly packed with no observable order.
Okay, thank you. So, as I just mentioned, if the hydrogen is replaced by the chlorine and the hydrogen replaced by this carbon 3 hydrogen molecule or structure over there, and is any way we can mix them together. So you generate something like a polyvinyl chloride and the polypropylene together or whatever, okay. Yes, you can do it, okay. So that's what we call a selective combination of the monomer, okay. So, so basically you have one type of monomer, okay, a mer over there, okay, which is this type. And then you have another type of the mer over there, like the one here. And then you combine them together, okay. And then you, if you only have one type of mer involved in the polymer, it's called homopolymer, okay. And then if you have 2 different types of mers involved in polymer materials, we call the copolymer over there. The copolymer is more or less like you have, it's not not exactly the same as the alloys we have over there. The alloy contains 2 different kind of elements and right, metallic elements over there. Here, so the mer basically you can consider as a one type of metallic element over there. Okay, so you have 2 different types of mers. You mix them together. Okay, so you have 2 different kind of elements. You mix them together for the metallic materials, and do you form a copolymer? That's what they call. Okay. Then depends how you will be arrange those molecular chains over there. Okay, all right. So once you connect all those mers together, you form a chain. Okay, And then how you will be arranged, because the one piece of the polymer will have millions of those chains, okay, over there, okay. So you can arrange those chains in some kind of order form, okay. Then we call this type of the polymer is a crystalline polymer. If you just mix them up randomly and throw them on the table or whatever, okay, and then these type of the polymer we call the amorphous polymer, okay. And homopolymer, copolymer, and crystalline polymer, amorphous polymer, all those structure change at the type of sort of merge change will affect the mechanical property down the road. Okay? Will affect the engineering performance down the road. James Alexander, you can just see a few words over this one, next one. Thank you.
The degree of crystallinity may range from completely amorphous with the less regular prisms of the image to up to 95% crystalline, which are the regular cone-shaped versions of the image. Presence of amorphous and crystalline regions in a polymer is analogous to a two-phase metal alloy. Polymers with molecular chains at large irregularity to attach functional groups makes it difficult to arrange uniform structure and therefore favor the amorphous. Polymers are rarely 100% crystalline, since it's difficult for all regions and all chains to become alike. So it's expected that the degree of crystallinity versus percentage, some physical properties depending on the energy, such as heat treating, which causes crystalline growth.
Thank you. So is there any way, okay, based on the arrangement of those molecular chains over there, we can have two different types. One is crystalline, another is amorphous over there. Is there any way we can mix them together again? Yes, you can. Okay, so you can have a polymer with certain percentage of crystalline and certain percentage of amorphous over there, and so you basically form a kind of semi-crystalline kind of polymer over there. Okay. So the degree of the crystallinity, okay, may range from complete amorphous up to the 95% of crystalline. Okay. The presence of the both amorphous crystalline, polymer is similar to the two-phase metals. So it's more or less like, but compared with the metals, for example, steel, the polymer structures, okay, a polymer are called polymer microstructures are much simpler, okay, compared with steel. Okay, steel will have so many different phases over there, right? Ferrite, pyrite, what is the cementite, and then the bainite, martensite, austenite, whatever. Okay, so many different phases, right? It will be confused very easily. Okay, but for polymer, you only have two different types. Okay, one is called amorphous, another is called crystalline. Simple down. Okay. And then if you have a functional group involved over there, so the hydrogen not those MERS do not contain like all those atoms as hydrogen atoms over there. You have chlorine or whatever the other molecular groups involved over there. Then those kind of polymer, you will be able to, most of them you will find them in like amorphous kind of structure over there. Okay, so the functional group, I just want to reemphasize the functional group basically it tells you the chlorine, for example, in this structure in this mer is called a functional group. Okay. Okay. Don't think the group means a lot of atoms over there. Here is basically chlorine itself is called a functional group, and then here in this mer over there, in the polypropylene over there, so the 1 carbon and 3 hydrogen over there, this is called a functional group over there. Okay. To determine how much of the crystalline polymer is involved in the polymer you are using over there, and then we use index is called crystallinity. Okay? And crystallinity is basically tells you how much, what's the percentage of the crystalline polymer is involved in your polymer. Okay, so and it depends, and if you have 50% of the polymer in the polymer you're using over there, they have the arrangement of those molecular chains in a crystalline form over there. Then we would call the crystallinity is 50% or whatever over there. Okay. If you have a question, just stop me. Okay. Suraj, no, Ahmed. Can you see a few words about this one, next one? Thank you.
Just similar to constant. Or once again, constant things or expansion or increasing the free fall occurs as the change in the crystalline state.
Thank you. So talking about the property now. Okay. So for polymer material, this property is very important. It's called viscosity. Okay, because polymer, when we process the polymer, and very often you have to use, like for example, for the thermoplastic and most of the automotive components, I would say, we use the plastic injection molding process to produce those automotive polymer components over there. So viscosity is a very critical material property for polymer. So for the crystalline polymer, and then this graph is basically show you how does the polymer, the viscosity of the polymer changes with the temperature. Okay. So if you increase the temperature, if you look at the horizontal axis, okay, and then once you pass the melting temperature of the crystalline polymer, and the viscosity will drop significantly. Okay, you have a big drop at the melting point. So, so crystalline and polymer has some kind of similar viscous behavior is like a metal over there. Okay, so at the melting temperature is so the crystalline polymer will change its phase because from the solid to become liquid over there. Okay, and so it can float very easily above the melting temperature. Okay. And so that's why they said it's similar to ice, and when ice melts, becomes water. Water will have a very low viscosity, and ice is a solid. Basically, it's like metal over there. Okay, and metal has a similar kind of behavior over there. Okay, and the second property is called the specific volume. Okay, so the specific volume stands for the volume per unit weight. Okay, okay. So basically, if you want to describe it, you can use a unit is, let's say, cubic meter over kilogram or whatever. Okay. So you basically have a unit weight, and then the volume will change as the temperature varies over there. Okay. So this graph here, the horizontal axis stands again for the temperature, and vertical axis stands for the specific volume. So if you increase the temperature, okay, the crystalline polymer will increase the volume with a fixed weight over there. Okay. Then once you pass this melting temperature, okay, then the polymer, the crystalline polymer, will increase the volume significantly. Okay, with the fixed weight over there. So again, has kind of similarity compared with the metal over there. Okay, so metal is solid. If you increase the temperature, it will increase the volume a little bit, not that much. But once you change its phase from solid to liquid, and the volume will expand quite a lot over there. For example, for aluminum, pure aluminum, you will have like 6-7% of the volume increase from solid to liquid over there. Suraj, are you there? No? Suraj, are you there? So viscosity and for amorphous polymer, okay? And so this graph will show you the viscosity change with the temperature for the amorphous polymer. So let's just review for the crystalline polymer. If you increase the temperature, and the viscosity will drop suddenly at the melting temperature. Go ahead. This one. This. You mean it? The Oh, you're talking about the viscosity, or you're talking about the volume here? Yeah. I believe that the increase of the temperature, even they become like liquid over there. And I think those polymers, those change structure over there, and in terms of the movement of those, because basically you have like the bonds over there, the bonding over there. Because for example, okay, you have the bonding over there. So for example, you have like two electrons, they share between the carbon and hydrogen, and between the carbon and hydrogen over there. Right? Those bonds, as the temperature further increases, even the liquid state, and those bonds probably will become loose over there as the temperature increased. And this kind of loose bond becomes loose, basically will result in a further increase of the temperature. At the high temperature, those electrons will become more active, I would say. Okay, will result in the further expansion of the. No, I think eventually it probably will be. Uh, uh, I don't know it will become a gas or not. Okay, and if your temperature high enough, maybe the bonds, because these bonds, okay, they are covalent bonds. Okay, for example, here, all these bonds are covalent bonds. You need a very high temperature to break them. Okay. Okay. Then if these bonds being broken over there, and then obviously it will be vaporized. The thing will. So you basically go back to. You go back from the polymer. You keep increase the temperature. Maybe those bonds were broken. You basically go backwards. Okay. So from the polymer, you go back to the monomer. Okay. And it'll become a gas solid. Okay. But you have to increase the temperature, give enough energy to break them for those covalent bonds over there. I believe it will happen if you keep increase the temperature. It's like a plastic, I mean, you give a lot of heat, it will generate the smoke, right? Right? It will be burned or whatever over there. So it will become like a kind of gas over there. Okay. So viscosity in amorphous polymer, okay. And so um, in general, amorphous polymer in a solid state is hard and brittle under the applied heat. The polymer will first transform to a softer laser state before forming a viscous liquid over there. Okay, and then the transition from the solid state to softer laser state occurs at the glass transition temperature. So for the amorphous polymer, those polymers, they do not have a clear melting temperature. But what they do have is what we call the glass transition temperature. So in other words, the viscosity of these type of polymer will change gradually instead of so dramatically at the melting temperature for those crystalline polymer. Okay, so the viscosity will change slowly, okay, as the temperature increased over there. Okay, there's no sharp transition in viscosity, okay, for these type of the polymer, okay, and so the behavior of the amorphous polymer compared with the crystalline polymer in terms of viscosity are quite different. Okay. And for the specific volume change with the temperature, amorphous polymer also behavior quite differently from the crystalline polymer. So if you keep increase the temperature, the volume will expand, okay, and then past the glass transition temperature, you won't have a very sharp increase in volume, but you will still have a gradual increase of the volume, okay, and maybe the increasing rate is higher than the crystalline polymer over there, but you won't have a sharp transition over there at the glass transition temperature for the volume change of the amorphous polymer over there. I think I'm gonna finish these two slides before I let you go. Okay. 35, 36 is Vinit. Can you just say a few words about 35, 36? Okay, thank you. So these three curves, okay, here, red, green, and I call it blue over there, okay? So for the red, is for another type of material. It's not a polymer, okay? We're talking about glass over there, okay? I believe that in Dr. Nee's course of the ceramics, they mentioned the glass over there, okay? So the glass will have a clear glass transition temperature, and the faster glass transition temperature, the specific volume increase will much faster than the specific volumes over there. And then for the crystalline solid, and you have melting temperature. So if the specific volume will be changed at the melting temperature quite significantly. And then for the semi-crystalline solid, because for the polymer, you can have maybe 50% of crystalline polymer and 50% of amorphous solid polymer over there. Then you're gonna have two different kind of transition temperature. One is called glass transition temperature, another is called melting temperature. So the specific volume for these type of semi-crystalline solid, semi-crystalline polymer, contains a certain amount of crystalline polymer and certain amount of amorphous polymer over there. You have two transition temperature over there. So once you go through each one of those transition temperature, the specific volume will change quite a lot, especially when you go through the melting temperature. The specific amount will increase quite significantly. And I think in terms of the bonding structure, okay, and which means reflecting on the mechanical properties, and polymer can be divided by three different types. Okay, and if just for mechanical guys, and you probably would just think about their properties different, quite significantly different, okay, among these three different types of the polymer. But from material guys, we say, no. The property is decided by the bonding structure, okay, by the microstructure, okay. Sounds like more scientific over there, right? It's a bonding structure, okay? Decided the mechanical property, okay? You don't just look at the things on the surface. You have to go deeper inside, okay? So the polymers can be divided by three different types, okay? I think it's mainly decided by the bonding structure over there. The first one is called a thermoplastic, and the second one called a thermoset, and the third one is called a elastomer, which is the real name is called elastic polymer. So in the short form, they take the elast, E-L-A-S-T, elast, and take one O out of the poly, and take the mer. Okay, so they call it elastome. Those are three different types. Okay, so I'm gonna stop here, and then I'm gonna see you guys Thursday morning this room. Okay, for the testing of the steel module. Okay. Any other questions? If not, I see you guys 9 o'clock in the morning in this room, okay?